This lecture is a review of some ideas from supervised machine learning that are very useful when thinking about neural nets and deep learning. So we're going to begin by talking about some common problems in supervised machine learning. So these are the regression and classification problems. Then we'll talk about a statistical framework for machine learning, which leads to optimization problems over classes of models using particular loss functions. Then we'll talk about why you choose certain loss functions in some cases, including the justification for square loss and cross-entropy loss in regression and classification respectively. And then we'll talk about model selection using the bias-variance tradeoff, leading to an unexpected twist from the recent developments of neural nets. So let's start with some common problems in machine learning, particularly supervised learning. So one problem is the regression problem, and this is the task of predicting a continuous valued output given some input. So mathematically, we could think there's some function f, which is a map from, say, Rd to R, but could be a map from Rd to higher dimensions as well. And we could say y, the observed data, is f of x plus some noise. And our problem is given a set of points xi, yi, let's say we have n such points, we want to find or estimate the function f. So visually, we can see this is like the problem of fitting a line through data. What is the best fit line through these data points? Now, another common problem is the classification problem, and that is, given a point, predict membership in some category. So for example, you could be given an image, and you might want to determine what the main content of that image is. For example, is it a cat, is it a dog, or something else? So here, our formulation could be that suppose there is some function f, which goes from Rd into a set of m categories. So here, d you could think of as like the number of pixels in an image, and then m is the number of categories that you've prescribed in advance. For example, with the ImageNet dataset, there are 1,000 categories. So what we're observing here is, say, some y, which is f of x, perhaps corrupted by noise, perhaps not, and given a set of xi's and yi's, so given a set of, say, images and labels, then we want to find the function f. So here, visually, we could see there's a bunch of x's and a bunch of o's that have a sort of two moons shape. And what we want to do is, for an additional new point, we want to classify, is it an x or is it an o? So this requires drawing some sort of decision boundary where on one side we say o and on the other side we say x, and we do this by the details of the particular function f that we are learning. Now, of course, this formulation is perhaps a little bit simplistic. For some images, there may not be obvious that every image corresponds to a particular category, and there could be some images that are right on the boundary between multiple categories, but this should be a good model to think about classification with. All right, let's think about some terminology, because in machine learning and in deep learning, there's many people use different words to describe the same thing. So what we've called x, we could call this the input variable. We could call this the predictors, because these are the quantities that you're making a prediction from. We could call these independent variables. Some people call them features. So here, the variable y, we could call this the response, or the dependent variable, or the output variable. And the goal of supervised learning is to predict the response given input variables, where we have a whole set of training data which have pairs of responses and input variables. So now f, we could call this the model, we could call this the predictor, we could call this a hypothesis. And here we see like some people may use the word predictor for f, some people may use the word predictor for x. All right. Now, with this terminology, we can talk about the statistical framework for machine learning in a supervised setting. And here, our framework is a statistical one, which means there is a probability distribution involved. So here in the supervised setting, right? We're dealing with pairs of data points, x's and y's. So these are the input variables and the responses to those input variables. We're going to assume that each xy pair is sampled from some joint probability distribution over x and y. Then we're going to assume that we have access to a training data set, and that's going to be some D, which is a set of xi, yi, and our key assumption here is that these are all independent, identically distributed samples from this joint probability distribution. So then also we're going to have test data, and then those are also IID samples from this same distribution. Right, so here the key assumptions is there is a distribution that our data is coming from, and our training data and test data are both samples from that distribution that are all independent from each other. So now a key aspect of the statistical framework for ML is that we're able to estimate the model or predictor by using maximum likelihood. And this maximum likelihood estimation is going to be the principal basis for choosing one predictor or one model over another. So usually this is going to result in an optimization problem that has the following form. So we're searching for some function f, we're going to get some function f hat, and that's going to be achieved by doing some minimization over a space of functions. And the objective that we're minimizing is the sum of data sets of some function of the predicted output for the input xi with the measured output of xi. So that function is going to be called the loss function. So here, the framework quite often yields minimization problems over the sum of terms where each term corresponds to a single data point, and that is a loss function applied to the response of a given training data point. Right? So in this formulation, L is our loss function, and this, for example, could be the square loss, where if you hand it a y hat, the prediction from this trained model, and y, the observed value of the response for some particular training data point, then that loss could be the square of the difference between these. And script H here we could call the hypothesis class, and this is something which is up for a user to decide. A simple hypothesis class could be something like the set of degree D polynomials. And maybe for certain assumptions on your data, that hypothesis class makes sense. In the more modern setting of neural networks, the hypothesis class is often defined a bit more implicitly, for example, as the set of functions that are expressible as a neural network. And it could even be defined more implicitly than that by saying like the set of functions that are described by neural networks, even giving, say, some early stopping criteria. Right? So nonetheless, there's some hypothesis class, some set of functions that are searched over to minimize the sum loss over the training data points. And so this leads us to two key questions. Right? What loss do you choose and why? And what hypotheses should you be searching over? Right, so on the first question about choosing loss, and one of the goals of this lecture is that you should be able to see why we use a square loss for regression in some cases, and a cross-entropy loss for classification in some cases. So that these are both based on reason principles, and that fundamentally goes back to maximum likelihood estimation under the statistical model from our statistical ML framework. So then we're going to talk about which hypotheses should you search over, and we'll think about the model complexity and how that affects the performance of predictors. All right, so first up, we're going to discuss linear regression and why that leads to a square loss, or to a choice of the square loss. Right, so let's set up our model. So let's say that we have some vector A in RD, and then we're going to consider data points X, which will also be in RD. Our model is that the response yi is equal to xi transpose A plus epsilon I, where epsilon I is a normal random variable with mean 0 and variance sigma squared. So here, under this model, we're saying largely that y depends linearly on x through the unknown coefficients A, though there is noise, and that noise is Gaussian. So here you'll notice that the Gaussian has mean 0, and the reason for that is if we were to model a different mean of the Gaussian, then we might prefer to just include that in the model itself. And so it's easier to work with this noise term, which has expectation 0. Now also, this Gaussian has variance sigma squared. This is something, this is a quantity whose value actually won't end up mattering. And so we don't need to know it in advance. Now the data, this script D is the collection of input and output variables, xi, yi, for the n data points that we have. Now, here the fundamental principle is that we want to choose the A by maximizing likelihood over the training data. So in order to do this, we need to determine what is the likelihood over our training data, and let's start with the probability density function of epsilon I. Because it's a normal of mean 0 with variance sigma squared, we know that its PDF is given by this standard formula, 1 over root 2 pi times sigma times e to the negative z squared over 2 sigma squared, and that lives for z between minus infinity and plus infinity. Now, we know that epsilon I, as per our model, is yi minus xi transpose A, and so we can actually evaluate the likelihood of any particular value of A given our training data. And so that we could write as, say, capital L of A is the product over I equals 1 to n of the likelihood function evaluated at each epsilon I, where we've plugged in yi minus xi transpose A. And here the reason that this is the product is because of the independence assumption over the training data. And this is where we've used that assumption. Now, generally we're going to want to maximize the likelihood. It turns out to be a lot easier to optimize the log of a likelihood instead of the likelihood itself. So let's compute that log. Here we see that the log of capital L of A is minus the sum of the square terms, yi minus xi transpose A, quantity squared over 2 sigma squared. And then we have a whole bunch of additional terms that are just constants in A. Right? So here we arrive at the important conclusion that we were going for, which is if we are to maximize the data likelihood, meaning maximize over A of L of A, then that is the same as minimizing the square loss. So that is minimizing over A of the sum from I equals 1 to n of xi transpose A minus yi quantity squared. Right? So under our framework, we're going to view this as the square loss applied to y hat equals xi transpose of A and the observed response yi. So here we also notice that the sigma squared from before, it doesn't actually affect which value of A is the best, and so we can remove that from the minimization. So again, our conclusion is because our noise model was Gaussian, then maximizing data likelihood is the same as minimizing the square loss. And this is the principle behind which we would choose the square loss when performing a regression. Now, if we had a different model for the noise of our measurements, our observations, then we might want to choose a different loss function. Right? So we shouldn't think regression always leads to square loss, but regression under Gaussian noise leads to square loss. And if we had a different type of noise, then we might want to optimize over a different loss. All right, so let's contrast this to the case of logistic regression and cross-entropy loss. So here, let's set up a data model. So let's say I have, again, some vector A in RD, and D is sort of the dimension of space that we're working with. And then now we're going to think about a binary classification problem. So let's say we have two classes. One is class 1 and the other is class 0. And so now, under our model from the statistical machine learning framework, at any given point x, there is some probability distribution over these two classes. We're going to assume that that distribution has a particular form. So let's say the probability that it's class 1 or category 1 given x is sigma of x transpose A, where sigma is the logistic function. So here the logistic function is sigma of z is e to the z over e to the z plus 1, which is the same as 1 over 1 plus e to the minus z. And it's something that's basically very close to 0 for large negative values, and it's very close to 1 for large positive values, and it smoothly goes in between these. So if this is the value for the probability that a point x is of category 1, then the probability it's of category 0 has to be 1 minus sigma of x transpose A. So again, as before, we're going to have some data set. It's going to be some set of xi's and yi's. Now, before we start trying to solve this, this problem and of getting at A, let's make sure that we understand the model of the data that we're working with. And so here is a visual picture of this model. So here there's some vector A, which we have drawn. And so it defines a hyperplane. In this case, the hyperplane, or in the two-dimensional case, just the line, where a dot x equals 0. If a dot x equals 0, then we're going to be fitting in, asking what is sigma of 0, and that's going to be a half, which means any data point which lies along this dark curve is going to be 50-50 chance of being class 1 or class 0. So this is going to be our decision boundary. Now, on the left of this curve, we're going to be more likely to be class 0, and on the right of this curve, we're going to be more likely to be class 1. So if we're very, very far to the right, we're actually very close to being, to having certainly the values 1, and if we're very far left of this curve, we're very close to certainly having the values all be 0. But this is still a continuously defined object. So if right on the decision boundary, we have exactly a 50% probability of being class 0, class 1, if we move a little bit from that boundary, now we have a close to 50% probability of being 0 or 1. So as it's drawn, this first row of data points just to the right is more likely to be 1s than 0s. Then that next sort of diagonal of data points is even more likely to be 1s than 0s. And then after that, let's say it was so likely to be 1s than 0s that we didn't even observe any 0s. And similarly on the other side. So what's drawn here is the shades of gray correspond to the likelihood that a point would be of class 1. And so for far left of this decision boundary, then it's basically 0. And for far right, it's very close to unity. Now, this problem, like we said before, it's continuously varying, right? The probability doesn't just suddenly change between being class 0 and class 1, right at the decision boundary. It smoothly changes, and there's a region over which that smooth change happens. And so we could say, for example, colloquially, this is like a region of uncertainty where if we're close to the decision boundary, then we have some probability of being in either class. And the closer we are to the boundary, the closer that probability is to a half. So we could even ask, what's the width of this region of uncertainty? And roughly, it's on the order of 1 over the L2 norm of the vector A. Right? So if A is a very, very large vector, then there's going to be a very sharp decision boundary. And if A is a very small vector, then there's going to be a very, very diffuse decision boundary. And you could imagine in certain applications, there are sharper boundaries than in other applications. All right, so again here, our point is that there's a decision boundary because of the assumption in this problem, it is linear. There's a width around the decision boundary corresponding to a region where there's reasonable uncertainty in the classification. But if you were pressed to decide the label at any given point, then you would just say, is the probability of class 1 greater than half? If so, call it class 1, otherwise call it class 0. Okay, so now back to our principle, where our principle was to estimate A by maximum likelihood. So in order to do this, we need to write down the likelihood function of a given A, provided that we know our training data. So capital L of A, we're going to write as the product of I equals 1 to n. In this case of the probability that yi equals 0 given xi raised to the 1 minus yi times the probability that yi equals 1 given xi raised to the yi. So here we're cleverly using some algebraic properties of the fact that we chose the classes to be 1 and 0, making this particular way of writing the problem particularly convenient. And again, we're also using the fact that all of our data points are presumed to be IID samples from the underlying distribution. So as before, we're not going to optimize likelihood directly, we're going to optimize log likelihood. So here the log of L of A is the sum over the data points of 1 minus yi times the log of the probability of yi is 0 plus yi times the log of the probability of yi equals 1. Before we interpret this as a cross-entropy loss, let's define cross-entropy. So the cross-entropy loss between two random variables, p and q, let's say these are discrete random variables over some state space z. This is minus the sum over z of p of z log q of z, or minus the expectation under p of log q. All right, so under this definition of the cross-entropy loss, then what we see is that maximizing the data likelihood is equivalent to minimizing the cross-entropy loss. So here, maximizing capital L of A is the same as minimizing over A of minus the quantity that we see at the top of the screen right now. And we can plug in our formula for what those probabilities were based on like sigma of xi transpose A. And then we can see this is indeed the cross-entropy loss, where we have to make sure to include the minus sign in part of the cross-entropy loss. Here's the cross-entropy loss between two distributions. The first distribution was yi comma 1 minus yi. This is a one-hot vector that's either 1, 0 if the data point was observed to be class 1, or it's the vector 0, 1 if the data point was observed to be class 0. And then the second term going into the cross-entropy loss is the probability distribution over class 1 and 0 under our logistic model. So we've seen that maximizing data likelihood under this, in this case of classification, is the same as minimizing cross-entropy loss under this particular model that we assumed. And we should note that the cross-entropy loss, it penalizes strongly data points of some observed category to which the model assigns a very low probability. And you can see that in the for example, in the log terms of the expression. And one thing that you should ponder is like, what really is the difference between like cross-entropy loss and square loss? Like, why couldn't we just have used a square loss even though we're doing regression? And you should think about like what the sources of these losses were and like how much they penalize different errors in data. All right, now we're going to move on to the second question that we talked about before, which is how do we think about what class of hypotheses we should search over? And there's a standard story from statistical machine learning which tells us how to think about this. Right? And that story is as follows. So we could envision a plot of error versus model complexity. So a model with very low complexity could be something with very few parameters. It could, for example, be a very low dimensional polynomial or a line. And a model with high complexity is something that has a lot of parameters, for example, a very high degree polynomial or a neural network with very, very many coefficients or very many weights, or there's a variety of other categories of models out there. Roughly speaking, increased model complexity increases the expressivity of those models to be broader in the class of all functions. So we're going to distinguish between training error and test error, right? So before we showed that there was this optimization problem that you could solve to estimate the unknown parameters in either regression or classification. And those parameters were estimated by optimizing the sum over data points of some loss function. Right? So that quantity itself we could call the training error. And because those are computed over the observed training data points. But we're also interested in the test error, which is if I collected a new data point, how much loss would I have? How much error would I have? Right? So let's look at the standard story. The standard story is that as model complexity increases, our training error decreases. So this is natural because if we have too low complexity of the model, we can't fit the true structure of our data. And then as we increase model complexity, we can fit the training data possibly exactly. And so as complexity increases, the quality of performance we have on training data decreases to 0. Now, what's interesting is the test behavior. So what's typically observed and the standard story is that if your model complexity is too low, your test error is high. As you increase the model complexity, your test error decreases. But then at some point, as you continue increasing the model complexity, the test error starts increasing and continues increasing thereafter. So here, then the name of the game is to try to find the point with the lowest test error, like where is the bottom of this purple U curve. And the story is that higher complexity models have lower bias but higher variance. And we're going to talk about the bias-variance trade-off in a second, but this will provide definitions to these terms. And so as higher complexity models have lower bias but higher variance, if the complexity is too high, then the story is that these models will overfit the data. The variance term is going to be very, very high, and that's what's going to dominate the test error. And so reaching this sort of conclusion that after a certain threshold, larger models are worse. So this is the standard statistical ML story, and it's something that has been challenged recently by recent developments in neural networks, which we'll talk about in a few minutes. So in order to explain this picture, we should address what is the bias, what is the variance, and what is the trade-off between them. And this is going to occur via something called the bias-variance decomposition. So let's work out the bias-variance decomposition in the case of a regression model with a square loss out of simplicity. So this model, we're going to assume that y is given by some function f of x plus a random quantity epsilon, where the expectation of epsilon given x is equal to 0. So here we're going to let script d be our data points, so this set of endpoints of xi, yi, and these are all IID samples under this model. Now, we're going to suppose that we have some algorithm for producing an estimate of f, for example, by solving the optimization problems that we talked about before. And this algorithm is going to give us some function f hat. Now, for the discussion here, we're going to pay attention to what happens what in the changes of f hat based on different data sets D So we'll actually call that the algorithm is going to take d and hand us the sum function f hat sub d. Right? So what we want to do is we want to evaluate how good is f hat of d, and we're going to do this by computing the expected loss on a new sample. So this we'll call the risk of f hat of d, and so that is the expectation over a test sample, xy, of f hat of d of x minus y quantity squared. So this reflects the square loss, our choice of the square loss. All right, so again here, risk is expected loss. Now we want to evaluate this expectation. It's going to depend on d. And so we'll have to study that dependence. And so what we'll do is we'll take an expectation over all d. So we're interested in the expectation over d of the risk of f hat of d. So that is the expectation over x, y, and d combined of the square of f hat of d of x minus y. So here let's note that in this expectation, x and y, those are test samples. And d, that's the set of training samples. And by our assumption, these are independent of each other. All right, so we're going to decompose this into three effects, something called bias, something called variance, and something called the irreducible error. So we're interested in the expectation over d of the risk of f hat of d. And so this is expectation over x, y, and d of, well, let's just plug in what is the square loss of the predicted value and the observed value. So the predicted value is f hat d of x, and the observed value is f of x minus epsilon. So this is the value at test time. And so this quantity is squared. And so we will expand the quadratic here in terms of the first term will be f hat of d of x minus f of x, and the second term will be the minus epsilon. And so FOIL this out and carry out the expectations. And we see that the cross term here cancels. And that is because the expectation of epsilon given x is equal to 0. And this last term is the expectation of epsilon squared. Because the expectation of epsilon is 0, then this quantity is the variance of epsilon. So what we see is we have a partial decomposition so far that the expected risk is the expectation of x, y, and d of f hat of d of x minus f of x squared plus the variance of epsilon. Now we need to write out the first term of the right-hand side here, and then we'll pull through the variance term at the very end. And so evaluating this first term, what we will do is we're going to condition on x. So what that is to say, fix x, and then let's evaluate the expectation of d, and afterwards we can then take the expectation over x. So we're interested in now the expectation over d of f hat d of x minus f of x. And it's actually this quantity squared. And so we can write this out by saying we're going to add and subtract the expectation over d of f hat d of x. So that's the natural quantity to think about. So we can write this as the expectation of the square of the sum of two terms, and then we're going to expand out that by FOIL, and then we're going to pay attention to the middle term. Right? So this middle term is the expectation over d of f hat d of x minus the expectation over d of f hat d of x times the expectation over d of f hat d of x minus f of x. So we notice that this second term does not depend on d, and so hence it can be pulled outside of the expectation on d, and then that last term directly has expectation 0, and so then this whole term goes away. Uh, so what we're left with is these two terms, this expectation over d of f hat d of x minus the expectation of f hat d of x quantity squared. And this is literally the definition of the variance of f hat d of x over d. And so let's remember we've conditioned on x. We've fixed some test x and then said what is, and this term is now what is the variance with respect to different training data sets D of the output of our predictor at x. And so then our other term is this expectation over D of f hat D of x minus f of x all quantity squared. So inside the square, this is a term that we would call the bias. So that is to say, f hat D, how far is it from f of x? Like it ideally should be on average equal to f of x, but that might not necessarily be the case. And so the deviation between it and f of x is its bias, and so we're going to see this term as the squared bias. Right? So putting all this together, we end up with a formula, a decomposition for the expectation over d of the risk of f hat. So now we're putting back in the expectations with respect to x that we had conditioned on before. And here that breaks up into these three terms, right? So the expected risk is this first term, which is the expected square bias of the estimate, where that expected value is computed over test positions x. Then we have the expected variance of the estimate, and then we have the variance of epsilon, which we call the irreducible error. So this is the three-term composition into bias, variance, and irreducible error. Now, the story from standard statistical learning framework is that the model expressivity, the number of parameters, the model complexity affects which of these terms are large and which of these terms are small. And so let's see an illustration of this. So let's give ourselves kind of like a very simple model to reason with. Suppose we're in one dimension and we have y is equal to x plus epsilon, where epsilon is some noise model, say like a Gaussian with small variance. So then we can see examples to the right of like what the true curve is and some somewhat noisy samples from that curve. Now let's say we had a low complexity model, and then let's think what happens to each of these terms. So let's take the lowest complexity model we could imagine, which is, let's say our model is that y is a constant unknown value. We just don't know what that value is. So y equals c. So if I sample a bunch of xi, yi's from this joint distribution, and then I find what's the best value of c according to a square loss, then I'm going to get something like the mean of my data, the mean of my values of y. And so then let's plot that in purple. So that unknown constant kind of plops it in the middle of the y values corresponding to the x values that we observed. And here we could say that, let's look at that first term, the expected squared bias of the estimate. Right? So for many values of x, f of x is going to be quite different from our model, and even the model in expectation over data. So here the bias is actually quite high because the signal just simply cannot represent the true data, the true idealized model under the data that it is trying to fit. Right, so here the bias is high, but the variance is low. And you could imagine that because if you sample many different data sets, then roughly speaking, if these data sets are large enough, then the average values of y are going to be in a relatively tight range. And so here the variance term is low, but the bias term is high. And so we see on the right two different pictures of two different samples where the we see their ability to represent the data is low, but the actual change in value of this low complexity model is low, even though they're very different samples that are acquired at different data sets. Now let's look at what happens if instead we have a high complexity model. So as an example high complexity model, let's say we have a 6th degree polynomial. And so I could say, given these same data points as before, let's fit a 6th degree polynomial to it, and I might get this like crazy polynomial that fits all of these points exactly. So then if I have a different set of data, then I might get this other 6th degree polynomial that fits those points exactly. And what we'll observe is that, roughly speaking, the expectation over data sets of our predictor f hat of d is quite close to f. And so in this case, the expected bias is low because in expectation over data sets, the function is actually correct. However, what we see is that the variance over data sets is actually quite high. And here, this is a famous problem in mathematics where using polynomials to fit data can actually be quite sensitive if the degree of that polynomial is too high. All right, so here's our example of a low complexity model with high bias and low variance, and a high complexity model with low bias and high variance. So ideally, we should choose something that's in between, that has the right complexity. In this case, linear models would be the right complexity, since that's what the data came from. All right, so this allows us to think about this standard statistical machine learning story. This is the figure that we saw before. And again, that story is there's some region where the model complexity is low, and this results in something called underfitting of the data. Right? So for example, our constant function was not able to fit the linear behavior that it was trying to model in our low complexity model before. But then if our model complexity increases too much, then we overfit the data. And here we see that in these 6th degree polynomials, that's not the true behavior under that model. The true behavior was linear, but it was able to fit the data exactly, and that is what we asked the model to do at training time. So the standard story is, like, if model complexity is too high, you overfit the data, you get poor performance. That's due to very high variance, which then dominates the test error. Now, this story has been challenged recently by recent developments in neural nets. And here is the modern story based on neural nets. So as before, if model complexity is too low, then training error and test error is high because you can't represent the data. So this carries through. And so as model complexity increases, the test error decreases and the training error decreases. As I continue decreasing model complexity, the training error, as before, is going to go to 0. And we know from many experiments with neural nets is that they can fit typically any data if they have enough parameters. And this means any data, even randomly labeled data over random data sets, can be fit exactly by neural nets. So the story of test error, so initially it decreases as model complexity increases, and then it can increase as model complexity increases. And so far, this is following the story of standard machine learning. But what's surprising is that if you increase model complexity further, to extreme values, the test error can actually decrease. And not only that, it can decrease below the best value that you achieve for low complexity models. Right? So we might say we have two regimes. One that's an underparameterized regime where the model isn't complex enough to exactly represent the data. We have an overparameterized model where the model is complex enough to exactly represent the data, and so it could overfit to it. But nonetheless, when we train neural networks in this overparameterized regime, we actually see very favorable test error. Right? So the perplexing things here are that like test error can decrease as the model complexity continues increasing, and it can be lower than the underparameterized regime. And this is a phenomenon called double descent, which roughly, if we want to turn this into a rule of thumb with neural nets, is the idea that larger models are better. And it's not entirely understood why this is the case, though there are some things that can be said. So first, this double descent behavior has been noticed in different classes of models. It's not just an effect of neural networks. And so that means this is a broader issue in the field of machine learning than simply neural nets, even though people noticed it because of neural nets. But also, it begs a question of how is it the performance can be so good when model complexity is so high? Right? The standard ML framework would say this should be impossible. The neural net can fit anything, so why would it fit the nice thing that you want it to? And a going explanation for why this would be the case is because the neural nets themselves have sort of biases built into them. They have some like regularization built into them where they prefer, say, nice, low complexity functions over higher complexity functions. The details of this understanding are still being built, but it shows that there's much that's exciting about machine learning, and much of our intuition has been challenged by the dominant behavior of neural nets, even in regimes of very, very large numbers of parameters.